everyone. Thanks for coming to this session. And today the work I'm going to present is printing imperfections that are geometric patterns that can improve the resistance of 3D printed steel plates. In recent decades, researchers and practitioners have been trying to introduce metal 3D printing in construction, such as this famous Arab connection for a tensegrity structure and a facade fixture in US. And these two cases were manufactured by powder-based printing method. And more recently, the MX3D footbridge in Netherlands that was made by wire-based manufacturing method. So the common methods that are currently being considered by construction industry are mainly based on powder-based material or wire-based material. And depending on the power supply, it can be classified as electron beam, laser, or arc welding. And all of these are associated with the different limitations, such as size limitation, printing direction, because most of the printing method cannot do overhands, and obviously also the cost. The welding is very expensive procedure and to build the large structures that can be used in civil engineering construction. And also the quality is also an issue that normally the welded structures have large residual stresses and also associated geometric distortions. So the main research focuses in the metal 3D printing construction mainly lies in understanding the mechanical properties, where we do a conventional structural test on straight plated structures, but that are 3D printed. And also structural engineers are trying to do shape optimization that can be 3D printed. And also the 3D printing technology is constantly evolving in mechanical engineering sectors to make sure that the quality of the print can be improved constantly. And my personal view in 3D metal construction is that thin-walled plates and shells will remain as the fundamental shapes, as seen in this figure, in the bridge next to it. And the stability design is very critical for such structures. So therefore, the main research aim of the current study is to look at the fundamental plates and trying to improve their resistances. And our design inspiration is shown in these slides here. So for example, for simply supported plate, the lowest buckling mode has the one transverse half wavelength plus one longitudinal half sinusoidal wave, which corresponds to a buckling coefficient of 4. But an analytical solution for higher order modes shows significant buckling mode resistance of coefficient of roughly 42. But these analytical solutions cannot be achieved in reality for a flat plate. So our idea is to introduce sinusoidal imperfections to force a higher mode of buckling or delay the lower buckling mode in order to achieve higher resistance. So this system, we believe, has some advantages, like that we don't need to change the boundary conditions and we don't need to add stiffeners, which complicate the fabrication process. And also we don't need to perform onerous topology optimization, and the aesthetic appearance for this wavy structure can be really nice. So this is the numerical model that we used to validate our idea to see whether the plate will buckle in the way that we defined. So we used the square hollow sections as it can model the simply support condition and establish symmetric, and is able to be tested in reality. And in each of this square area, which is repeated in the stub column, we use the different wave combinations. So for example, in this case, the N represent the number of half sine waves in the transverse direction, which is 3 for this case, and m represent the number of half sine waves in the longitudinal direction, which is 2 for this case. And the corner region remained as a right angle. And the square hollow sections has a length of 3 times the width. And we use the S4R element, shell element, with the mesh size of half wavelength over 10 from a mesh sensitivity study. And the material model we used is a S316L stainless steel with a yield strength of 450. That is manufactured by power-based fusion method obtained from a previous study. We did the LBA analysis and the GMNIA analysis to investigate the plate buckling response under linear and nonlinear condition. And we tried the different wave combinations, including 1, 2, 3 transverse waves, half transverse waves, and 1, 2, 3 half longitudinal waves. And this gives 9 cases, and plus a reference case with the straight plates, that is N0 and M0. So in total, we investigated 10 cases of different imperfection amplitude, from small imperfection of 0.25 millimeter to a large imperfection of 8 millimeters. And we also modeled the different slenderness to see the effect of waves and the imperfection amplitude at a different slenderness range. And under linear bifurcation analysis, this table plots the failure modes of specimens with 2 longitudinal half wavelength at 1, 2, and 3 transverse half wavelength at different imperfection amplitudes. So in general, for all the cases, when the imperfection is small, the failure modes is typical plate buckling failure modes for square hollow sections, stop columns. And as the imperfection increases, the buckling wave gets smaller and also higher in numbers for the first case, which are all associated with increased buckling load, as can be seen in the next slide. And the figures here plot the critical buckling load for all the models. And the critical buckling load is transformed into the plate buckling coefficient, which is 4 for straight simply supported plates, as plotted as the gray surface in each figure. And overall, increasing the longitudinal wave number can increase the buckling resistance significantly, as you can see by comparing the green, yellow, and the red surfaces in each of the figure. But increasing the transverse wave number by comparing the same color but in the 3 figures, we can see that it doesn't have a clear trend. And if we look at the GMNIA result, this slide shows the load axial displacement curve from the GMNIA analysis. And for different slenderness and the combinations of waves, the effect of imperfection can be different. So for this case, with 1 transverse and 1 longitudinal half wave at a stocky cross-section slenderness, increasing the imperfection will reduce the resistance. But for this case, with a more complicated wave combination and at slender cross-sections, increasing the imperfection will actually increasing the load and also the ductility. And this slide shows the failure modes from GMNIA result for 1 longitudinal half wave and 1, 2, 3 transverse waves in a squared space. At 2 slenderness, which is 20 and 60, at small imperfection 1 millimeter and a large imperfection 4 millimeters. So we can see that for stocky sections with small imperfections, the buckling mode is the typical plate buckling or the elephant foot buckling. And as the slenderness gets higher and amplitudes gets larger, the buckling modes gets more complicated and can be associated with a higher resistance. So we can also look at the ultimate load surface plot, where the green, blue, red curves corresponding to 3-to-1 transverse half waves, and the 3 figure corresponding to 1-to-3 longitudinal waves. And the gray surfaces in each figure represent the Eurosteel design line, which is very close to the case of M1, N1M1, which is normally adopted for conventional steel research. And we can see that increasing the longitudinal wave number by comparing the same color in 3 figures, that it can reduce the resistance, so it's not recommended. And the best case is the N3M1 and N2M1 with imperfections smaller than 4 mm and higher than 4 mm respectively, at very small weight increases. So for example, for N3M1 case with the imperfection of 10 mm has 50 resistance increase compared to the design value, conventional design value, but at only 5% increase in weight. And for the current study, we recommend to adopt the imperfection pattern of N2M1 or N3M1 with the imperfection amplitude of 2 to 6 mm, because we don't want to make the imperfections infinitely larger, and also for the very small imperfections, we have the printing quality limitation. So as a conclusion, we see that we can apply the sinusoidal imperfections to increase the buckling resistance of steel plates, and the compression and the magnitude really depends on the plate slenderness. And also including longitudinal waves are not beneficial for the nonlinear resistance. And N2M1 and N3M1 with the imperfection between 2 to 6 mm are recommended for the studied case. And the weight increase is minimal for a relatively large increase in resistance. And the future work would include experimental tests that we already produced the specimen to validate the numerical results. And we need to normalize the imperfection amplitude as it's currently defined in terms of absolute value. And we also want to look at other steel grade, other boundary conditions, and the loading cases. Thank you very much.